So in this unit, or in this subtopic, we are supposed to learn about the design of reinforced concrete slab. And when we're looking at the reinforcement concrete slab, we are supposed to design it according to BS 8110. And generally, there are two main types of the slab that we're going to deal with. One of them is called the one-way span, and another one is called the two-way spanning slab. So generally, a slab is a plate of element that is forming the floor and the roof of a building, which is normally carried or which normally carry uniform distributed road. And in this case, I'm not going to measure on other type of the slab, but generally we are going to only consider two types of the slab. One is called one-way spanning slab, and another one is called two-way spanning slab. So we are only going to discuss about the two. In the design of the slab, there is something that is called the elastic analysis, and this is this only cover three techniques. That is idealization into the strips or the beams, whereby we are going to look at a slab as a series of beams that are joined together. Then we are going to look at the elastic plate analysis. We are going to look at the analysis, and then we are going to look at the infinite element analysis, and we are going to do it in detail later. Then in the design, we are also going to look at the design coefficients, the coefficients that are used in the design of the slab. And also we are going to look at the yield line method of the design. So without wasting a lot of time, I would like to look at how you can be able to design a one-way slab. And in the design of a one-way slab, there is something that we are going to start with the idealization for the design. And in this case, we know that one-way slab is carrying predominantly uniformly load and designed on the assumption that they consist of a series of a rectangular beam, which is 1 meter wide, spanning between the supporting beams or walls. That means that when we are designing a one-way slab, we are going to design the slab in a manner that we are going to visualize that slab as a series of beams that are joined together, and each beam has breadth, or it has a width of 1 meter. So when we are designing a one-way slab, or when we want to design, we need to know that for a one-way slab, the Ly of Lx, that is Ly is the effective length for the longer section, and Lx is the effective length for the shorter section. So if you divide Ly with Lx, you are supposed to get the answer being greater than 2.0, so that our slab can be a one-way slab. Otherwise, if it is a less or equals to 2.0, then that is a two-way slab. So Lf is the shorter effective span, as you can see, and Ly is a longer effective slab, as we are going to see. We are going to look at this in detail when we come to class. Yeah, this is a continuous one-way slab. We know that continuous, it has multiple sections or multiple support sections, as you can see. And yeah, so when we are designing a one-way slab, the first thing that we need to know is to categorize the span as either one-way or two-way slab. How do we do it? First of all, we need to determine what is the value of Ly and the value of Lx, that is Ly is for the longer effective span, and Lx is the length for the shorter effective span. So that is the first thing. We determine what is the value of Ly and what is the value of Lx. Then from there, we are supposed to divide Ly over Lx. If it is greater than 2.0, then our span will be called one-way span. The second step in the design is whereby we are supposed to size our span or our slab. And in this case, we should know that the value of D, which is the effective depth, is going to be given by Lx, the shorter effective span. You divide by 30. You divide by 30. By doing so, you will be able to obtain that D should be greater or equals to Lx over 30. Then from there, we need to determine what is the value of H. The value of H that we are supposed to determine is the overall depth. Remember, I said that D is effective depth, while H is the overall depth. In order for us to be able to calculate H, you need to use the formula as you can see. That is, you need to use that formula as I have highlighted. So, you have the value of D as you have calculated, which is Lx over 30. Then you know the cover. The cover is, you know about the cover as we did in the beams. You know about the tolerance. Tolerance will always be 2.5 millimeters. And diameter over 2 is whatever you can see. That is the diameter over 2, diameter over the reinforcement. Then step number 3 is whereby you are supposed to compute the design load, moment, and the shear. When we are doing the design for the load, the moment, and the shear, one thing that you need to know is that for a one-way span, the same procedure that we did during the design of a beam is exactly the same procedures that we are supposed to use in the design or the computation for the load, for the moment, and for the shear in case of a one-way span. Therefore, the W, that is the design load, is going to be given by 1.4 GK plus 1.6 QK. Then we need to be able to design for the moment and the shear forces. This is done exactly the same way we did with the beam in case of a single, that is a one-way span. Then from there, you need to go to step number 4, whereby we design for the tension reinforcement. This is going to follow the same procedure as in beams for the moment still, and that the distribution bar will be 0.13% of BH, that is AS minimum. So this exactly the same way that we designed the beam is exactly the same procedure that we are going to use in the design for tension reinforcement in case of a one-way span. Then from there, we need to go to step number 5, which is check for the shear. And in check for the shear stress in the slab, 1, we need to design the shear stress. That is, remember, this is exactly the same formula that we used in the design for the shear in case of beam. That is V maximum, which is the shear force, divided by B times D, which is the cross-sectional dimension. Then from there, we need to compare with V with 0.8 root of FCU, all 5 Newton per millimeter squared, whichever is less. Remember, that is exactly the same thing that we did in the design of beam. And then from there, you need to, after comparison, you need to check which is smaller than the other, that is between 0.8 root of FCU and 5 Newton per millimeter squared. The one that is smaller, you are then supposed to compare with V. Then the procedure continues as we did in case of the beam. Then from there, we need to check for the deflection. When we are checking for the deflection, in the case of a one-way slab, we are saying the same procedure used or is used as for the case of the beam. That is, you need to have the modification factor formula. Then from there, after modification factor formula, you need to know how to determine the actual Lx over D and also the one that you have calculated. Then from there, you need to determine what is there. That is, you need to mind if the deflection is okay or not. Exactly the same thing that we did. Then you need to check for the shear. And for the slab, in case there is no in no case should the clear spacing between the bars exceed the lesser of 3 times the effective length, or 750. In addition, the slab depth does not exceed 250 for grade 250 millimeters reinforcement. We are going to see it in detail when we go to that point. So that is exactly how you can be able to design for a one-way slab. That is how you can be able to design for a one-way slab. We are going to do this example when I come to our online class or our face-to-face class. We are going to do this example so that we can be able to understand how you go about doing a one-way span. Then from there, this is the table that we are going to use. We need to go to the how you can be able to design a two-way span. The design of a two-way spanning solid slab according to PS 8110. One thing that you need to know is that the procedure is more or less the same that we have already done in the span. First, you need to determine what is the value of Ly and the value of Lx. And from there, you need to know how to compute, or you need to compute the ratio between Ly and Lx. If it is less or equals to 2.0, then it is a two-way spanning solid slab. Then from there, you need to determine the support condition in this case. You need to determine the support condition in this case. That is, you determine if it is a continuous beam or it is a discontinuous hinge beam. That is the support condition that that your slab is being supported. You need to determine the type of the support condition. Then from there, you need to know how to size that two-way spanning. That is, you find the value of D, which is greater or equals to Lx over 30. Then from there, you need to find the value of H using that formula that you see there. And you need to know that tolerance will always be 2.5, and that the values of V will be from 125, 150, 175, all the way, and the maximum value of each should be 200 millimeters. Then from there, you go to step number 3. In the step number 3, you need to compute the design load. And here I'm saying that when you are computing the design load, you are using the same procedure as you did for the case of the beam. That is, the design load is going to be given by W is equals to 1.4 GK plus 1.6 QK. Then from there, you need to determine the design moment. In this case, you are determining the moment in X axis using the first formula, the one that I have highlighted, whereby it's a positive moment mx at the midspan. Then from there, you need to determine the positive moments my at the midspan using the formula that I have highlighted. I'm going to see, or I'm going to show you how to go about it during our face-to-face class. Then from there, you need to obtain appropriate moment coefficients, that is the B as X and B as Y from the table that is attached in this, that we are going to see the table that it's attached here, or the table according to BS 8110, the table 3.14. Then after doing that, you need to design for the tension reinforcement. When we are designing for the tension reinforcements, you need to know that the same procedure as in case of the beam is the one that is used. But then what we are doing when we are designing for the tension reinforcement, we are filling in this table. And that is, we have the X. That is the first column is for the position, whereby you have X continuous and X midspan, Y continuous and Y midspan. I'm going to show you tomorrow or during our face-to-face class. Then from there, you need to know how to determine the moment coefficient, that is BSX and BSY, the second column. In each case, you need to determine those moment coefficient, that is for the X continuous, X midspan, Y continuous, and Y midspan. And these coefficients, they are obtained from the table as we are going to see, that is table 3.14 from BS 8110 that we are going to see here. Then from there, you need to calculate the moment that is the positive moment, and also the that is positive moment at the midspan, and also positive moment at that is the negative moment at the continuous edges, that is for mx and my, as we have seen from those formula that are used to compute the moments. Then from there, you need to find the value of K, as we're going to see. You need to find the value of Z, the value of AS required, the value of AS minimum, which is 0.13% of BH, and then you need to find the value of AS provided from the table. We are going to see how you can be able to use this table in order for you to be able to determine the tension reinforcement. After that, you need to go to step number 5, whereby we are checking for the shear. In checking for the shear, you need to compute the shear, that is to compute the design shear. One, you need to compute shear at the support using the two formulas, as you can see. One, shear at the X continuous and X discontinuous. You use that formula, the first one. Then shear at the Y continuous and Y discontinuous, you use the second formula. That one we are going to see during our face-to-face class. But the moment coefficients, as you can see, they are being obtained. That is the moment coefficient in case of the shear. They are being obtained from the table 1.3.15 according to BS 8110. The table is still attached in this case. Then after determining the design shear, you need to calculate or design shear the stress. You need to determine the shear stress. In determining the shear stress, what you are doing is that you need to calculate the design shear stress by use of the equation of V maximum, that is the shear force, divided by the cross-sectional area, which is BD. And in this case, V is the ultimate shear stress. B is 1000. We say that we are designing as per 1 meter width. Then D is the effective depth, the one that we have just determined by sizing our beam. Then from there, you need to compare with 0.8 root of FCU or 5 Newton per millimeter squared, whichever is the less. Then this is the shade for the summarized table for the when we are checking for the shear. The first is there for the location. We are going to see how to go about it. Then the coefficients, then the shear. Then you compare with the V, you compare with the 0.8 root of FCU, then you make the necessary marks. Then from there, you need to go to step number 6, whereby you are checking for the deflection. And the deflection in case of one-way or two-way spanning is done the same way as we do for the beams. Therefore, they don't have any difference. Then from there, you need to check for the crack or the cracking. And the same way we have done for the case of one-way slab. That is, in no case should the clear spacing between the bars exceed lesser of 3 times the effective depth of 750. And it should not exceed 250 for grade 250. That is exactly the same thing that we are going to do. Then I'm going to give you, during our face-to-face class, I'm going to give you this formula, this question for you to be able to carry out the assignment effectively. So this is exactly what we are going to see. Thank you. I appreciate your time. God bless you. Nice day.